And I'm going to talk about AI for large imperfect information games, and in particular on how we made an AI that beat top humans in no-limit poker. Okay, so for starters, this talk is going to be about imperfect information games in general. I'm not going to talk about perfect information games like chess or Go. It will be applicable to poker, but also more generally, any sort of strategic interaction that involves hidden information. For example, security interactions or negotiations. And I think this is really important for bringing AI into the real world because the truth is most real-world strategic interactions involve some amount of hidden information. So when it comes to these games, poker has served as the primary benchmark challenge going back decades. In fact, if you look at the original papers on game theory, pretty much the only application they talk about is poker because it so accurately captures the challenge of hidden information. And in particular, there's a variant of poker called Heads Up No Limit Texas Hold'em that has sort of emerged as the primary benchmark for these games. Heads Up No Limit Texas Hold'em is a massive game. It has about 10 to the 161 different decision points. It is also the most popular variant of poker in the world. For example, No Limit Poker is the game that is played. No Limit Texas Hold'em is the game that is played at the World Series of Poker main events. And every year, the winner is determined by Heads Up No Limit Texas Hold'em. It's also featured in popular movies about poker, for example, Casino Royale or Rounders. And in some ways, you could argue it's the purest form of poker. It's kind of subjective, but it is a very strategic game. Whether you win or lose is entirely up to your skill. It's not up to the other players at the table, except for your one opponent, I guess. So there's no kingmaker effects, for example. And no prior AI has been able to beat top humans in this game. That is until 2017. So in 2017, we organized something called the Brains versus AI Challenge. We created an AI called Libratus, which we played against 4 of the world's best Heads Up No Limit Texas Hold'em specialists in the world. These are all people that make about 7 figures per year playing this game online. So we played 120,000 hands of poker over the course of 20 days, and there was a $200,000 prize pool divided among the pros to incentivize them to play their best. So they weren't risking money, but how much money they won depended on how well they did relative to the other players. So obviously, if you're familiar with poker, you might not have heard of these pros. So I wanted to say a word about how strong these pros are, because it really is important to play against the top players. And unfortunately, there are no objective rankings of professional poker players. But like I said, these are all players that make millions of dollars a year. And in fact, here's a question from the poker subreddit where somebody was asking how good are these players that we're playing against, and somebody responded, these players will absolutely trounce all the 2000 heroes that you might have heard of. The heroes from 2000s would be Division III college players, whereas these guys are all-star caliber pros. So this is a pretty accurate description, I would say. So there's a big skill difference between the pros that you see on ESPN and these guys who actually play this game for. The guys that you see on ESPN are basically celebrities. These guys are the guys that actually make a living playing this game. Okay, and the final result is that Libratus beat the humans in this game by a lot. The victory margin was 147 millibig blinds per game, which is a measurement of win rate in poker, which unless you're an actual poker player doesn't mean much. But to give you some perspective, this is about 3 times the win rate of a top pro versus an average pro. It was statistically significant at about 4 standard deviations, and each human lost individually to the AI. And this was a big surprise to everybody. In fact, when we announced the competition, there was a betting market on the outcome because, it's the poker world, and obviously they like to gamble on these sorts of things. And when we first announced that we were going to do this competition, the betting odds were 4-1 against us. And in fact, even after we won on the first day, the betting odds were still 2-1 against us. And I don't think it was until like the 3rd day that the betting odds were even. And by the 8th day, you couldn't even bet on the outcome of the competition anymore. You could just bet on how much each human would lose on each individual day. Because it was clear at that point that this AI was going to win. And in fact, even if you asked us, we were not very confident that we would win. I put our odds at about like 60%, maybe 65. But I did not think we would have a blowout victory like this. Actually, after this competition, we did another competition against these Chinese pros. So basically, somebody called Kai-Fu Lee in China called us, and he said, we would like you to do another competition in China against Chinese players. We'll broadcast it. It'll be a lot of fun. And we were like, well, why should we do this? We just played against the top humans. These Chinese players are not as good. And he said that he would pay us. So, we said, okay, great. So we played 36,000 hands against 6 Chinese players. We beat them by even more than we beat the top humans in America. And that was actually a huge hit in China. It was watched live by millions of people during that competition. They had really nice production value. You can see a poster like this. It was way better than what we did in America. All right. So why are imperfect information games so hard? After all, we have AIs that can beat humans in games like chess. We have AIs that can beat humans in Go. And in fact, you might have heard recently about AlphaZero, which can beat humans, well, is essentially superhuman in chess, Go, and shogi, all using the same algorithm. So what is it about imperfect information games that are so difficult? And one of the major challenges, not the only one, but one of the major ones, is that in an imperfect information game, the optimal strategy for a subgame, for a part of the game, cannot be determined in isolation. It cannot be determined using information in just that subgame alone. So let me show you what I mean. Oh, before I get to that, deep learning has taken a lot of credit recently for a lot of the breakthroughs in AI. Actually, our AI did not use any deep learning, no deep learning at all. But I would also argue that a big reason for why all these AIs are superhuman in various games like chess, Go, backgammon even, is because they use real-time planning. The planning component is huge. In AlphaGo, for example, it used Monte Carlo tree search. In Deep Blue, it used alpha beta pruning. So, in fact, if you look at AlphaZero without real-time planning, I guess this is kind of washed out, but it ends up being right around there without Monte Carlo tree search during real time. And top human performance is right around here. So, in fact, without Monte Carlo tree search, AlphaZero is not superhuman. The tree search gets you 2,000 ELO addition. So real-time planning is really important, not just in Go, but also in poker, it turns out. And this is actually the key breakthrough that allowed us to beat top humans, is figuring out how to do real-time planning. But it turns out that in poker, it ends up being way harder, which is what I'll get to right now. So in perfect information games, you take some action, your opponent takes some action, you find yourself in a particular subgame. And now you can forget about everything that came before, all the other situations you did not encounter. The only thing that matters is the situation that you are in and the situations that can be reached from this point on. And it turns out that in imperfect information games, this is not true. In imperfect information games, So in perfect information games, so for example, if I were to show you this chessboard, you don't have to know how we ended up in this situation. You don't have to know about the Sicilian defense or the Queen's Gambit. You can just look at this board, and if you're white, you can say, okay, well, if I do a search, I can see if I move my white queen there, then it's checkmate, and the game is over. So I should just do that. You don't have to know anything about the strategy of chess. But in imperfect information games, if you take some action, and your opponent takes some action, and you find yourself in a particular subgame, now some other subgame that you are not in, and in fact, you might not even be able to reach from this point on, can affect what the optimal strategy is for the subgame that you are in. And this is kind of counterintuitive, but I'm going to give you a concrete example in a little bit that illustrates this. Now, before I get to that, I want to talk a little bit about what our goal is in these games. Our goal is to find a Nash equilibrium, which in two-player zero-sum games is the same thing as a min-max equilibrium. I won't get too technical about the definition, but basically, in a two-player zero-sum game, if you are playing the Nash equilibrium, you are guaranteed to not lose an expectation. Now, it's not always easy to find a Nash equilibrium, but it's always guaranteed to exist in a finite two-player zero-sum game. So, for example, in rock, paper, scissors, the Nash equilibrium is to just mix randomly between rock, paper, and scissors with equal probability, because if you do that, then no matter what your opponent does, you will not lose an expectation. Now, in rock, paper, scissors, that also means you're not going to win an expectation, but in a complicated game like poker, where there's a lot of suboptimal actions that aren't part of the, aren't actually played under the Nash equilibrium, it's likely that your opponent will make mistakes, and you will end up, in practice, winning as well. Yes?
How important is it going to be that this is a two-player game for you? So if I compare this to, say, Heads Up, or not, if I go out of Heads Up, if I go to sort of thinking about, like, just sort of no limit, 7 players.
That is a great question. So I'll get to this, I guess I could talk about this now. In poker, it doesn't really matter. So in poker, if you were to use these same techniques for, like, 6-player poker, you would almost certainly win. That said, in general, like, poker's kind of a special game because I don't know if you play poker, but for two special things about poker. One is it's really hard to collaborate with other players. So you can't like say, hey, let's team up against this other person at the table. In fact, if you try to do that, that would be against the rules of poker. The other thing that's kind of unique about poker is that people fold in the game. So even if you have 6 players at the start of the game, after it very quickly comes down to 2 players because people fold. So you can use these techniques that are only guaranteed for 2-player zero-sum games, and it will just work in 6-player poker. But A big challenge is extending these techniques to other games that do allow for collaboration. And in that, we don't really have a good approach for those games yet. So for now, I'm just going to assume that we're working in the two-player zero-sum setting, and this does extend in some cases to other situations as well. Okay, so our goal is to find an approximate Nash equilibrium. We're going to measure performance in terms of exploitability. This is, you could sort of think of it as distance from a Nash equilibrium. It's how well we would do against a worst-case adversary relative to if we had played a Nash equilibrium instead. So how exploitable we are. And I would argue that exploitability is actually extremely important and has been overlooked in the AI community as a whole. And I think two recent man-machine matches actually really highlight this. One is the OpenAI 1 versus 1 Dota 2 matches that you might have heard about, and the other is Fanhui versus AlphaGo. In the OpenAI matches, they made this AI that was able to beat top humans in 1 versus 1 Dota 2 over 3 games. But after they won against the top human, they actually opened it up to the public and they invited random, mediocre players to play against it to see if they could find any weaknesses. And in fact, pretty quickly, within like a few thousand games, weak players were able to find certain tricks that they could, basically fool the AI and figured out how to exploit it and beat it. And also in Fanhui versus AlphaGo, so they famously beat Fanhui 5-0, but then after they published the Nature paper, they invited him to play several more matches against it to see if he could find out any weaknesses in the AI. And in fact, he was able to find weaknesses where he was able to consistently beat the AI, and they had to patch this before their Lisa Doll match. So I think what this really demonstrates is that it's not enough to beat top humans in 3 or 5 or even 10 games. You really have to be able to consistently beat top humans, especially if you want to deploy an AI into the real world, right? If you're Microsoft and you're trying to deploy this product, with real users, there's, millions or billions of them. If there's a weakness, they're going to find it. But with our AI Libratus, we played the top humans not just in 3 or 5 hands of poker. We played them in 120,000 hands of poker over the course of 20 days. And that whole time, all 4 players were working as a team to try to exploit the AI in any way they could find. And in fact, I actually I had lunch with one of the players just a couple months ago, and he said that the thing they found most shocking about the competition is that at the end of each day, we gave them a log of all the hands that were played, and we told them what the bot had on each hand that was played. And this is big because in poker, a big part of the game is actually keeping your strategy hidden. You fold if you fold, your opponent doesn't see what cards you have, and in fact, even if you don't fold but you lose the hand, you still don't show what your cards are. So you only see your opponent's hand about 20%, 25% of the time. And so like poker players will sometimes even call just to see what their opponent had. But here, we're just giving them that information. We're telling them what the bot had on every single hand that it played. So they didn't have to worry about that part at all. And they found it absolutely amazing that they could not figure out how to exploit the AI, even though we were showing them the hands that the bot was playing every single time. And the bot strategy wasn't really changing that much between days. All right, so I think exploitability is extremely important. I think it's been overlooked by the AI community. And this is something that the Imperfect-Information game solving community has focused on throughout its existence. All right, so now I want to get to the example of why Imperfect-Information games are hard. I'm going to talk about a simple example that I call coin toss. It starts with a coin flip. So a coin is flipped, it lands heads or tails with 50-50 probability. Player 1 is going to observe the outcome of this coin toss, player 2 is not. So after this coin lands, player 1 has a choice. They can either sell the coin or they can choose play. And we'll say if they choose sell, it leads to some separate subgame, the details of which are not important. The only thing that's important is the expected value. So we'll say if the coin landed heads, then the coin was lucky, and they can sell it for 50 cents. On the other hand, if the coin landed tails, we'll say it's unlucky, and player 1 loses 50 cents by selling it. On the other hand, they can choose play, and if they choose play, then it leads to player 2. And player 2 has to then guess how the coin landed without having observed how it actually landed. So if they guess correctly, that is player 2 guesses heads and the coin actually landed heads, then player 1 is going to lose $1 and player 2 is going to gain $1. And here the payoffs are shown for player 1 because this is a 2-player zero-sum game, so player 2 just receives the opposite payoff. Now on the other hand, if player 2 guesses incorrectly, that is they guess tails and the coin actually landed heads, then player 1 gains $1 and player 2 loses $1. And you can see there's a dotted line between the two player 2 nodes. This signifies that player 2 is in what's called an information set. This means that player 2, because they did not observe how the coin landed, they do not know which of those two states they were actually in. So I want you to imagine that you are player 2 in this game. And, so I want you to imagine that you're player 2 in this game. You've just observed player 1 choose this play action. And so you know that you are in this imperfect information subgame. So what should you do? Should you guess heads or should you guess tails? Well, one option is to just always guess heads. But if you do that, that's obviously a really bad strategy, because now player 2 can just sell the coin when it lands heads and get 50 cents, and choose play when the coin lands tails and gain $1. So on average, they're gaining 75 cents. On the other hand, you could always choose tails, but that's also a really bad idea, because now player 2 can choose play when the coin lands heads and gain $1, and choose tails when the coin sell when the coin lands tails and lose 50 cents, but that's better than losing $1. So on average, they're still getting 25 cents in this game. So it turns out that the optimal strategy is to mix. It's to guess heads with 25% probability and tails with 75% probability. And if you do that, then no matter what player 1 does, the best they can do is just break even, get on average $0 in this game. So this is the Nash equilibrium strategy for player 2 in this game, at least for this subgame. But now let's say we change the game a little bit. Let's say we change the payoff for the sell action. So now in expectation, player 1 loses 50 cents for choosing sell when the coin lands heads, and gains 50 cents for choosing sell when the coin lands tails. Well, it's pretty easy to see that as player 2, your strategy in this subgame should now change as well. Now you should be guessing heads with 75% probability and tails with 25% probability. But you can see what's happened here is that by changing the expected value of the sell action, we have affected what the optimal strategy is in the play subgame, even though the sell action is not part of the play subgame, and in fact it's not even on the path leading to the play subgame. So this is something that happens in imperfect information games. It does not happen in perfect information games. In perfect information games, if you wanted to determine the optimal strategy in a subgame, you only needed to look at that subgame by itself. But in imperfect information games, you have to look at the game as a whole. So you can kind of think of like perfect information games as a special case where you don't have to worry about all this stuff. Imperfect information games are the more general case where this is a problem. Okay, so what do we do? Well, it turns out that we don't actually have to know the strategy for the entire game as a whole. I mentioned that this sell action leads to a subgame where both players might take actions, but you don't have to worry about that. The only thing that really matters for determining the optimal strategy in this play subgame is the expected value of player 1 choosing sell. So what we can do is try to estimate what that value is to player 1, and if we have that, then we can determine the optimal strategy in the play subgame. And so that's what we actually did in Libratus. We also have a theorem that says if this estimate is within delta of the true Nash equilibrium value, then we can solve for the play subgame and get within delta of the Nash equilibrium. So in Libratus, we actually do this. We have this massive game, which is simply way too large to solve up front. So we come up with a really good strategy just for the early part of the game. And we estimate what the optimal strategy is and what the expected values are in the later parts of the game. And now when we're actually playing, when we find ourselves in a particular subgame, we come up with a much better strategy for that particular subgame using information about the expected values from the other subgames. And then we repeat this process. We just come up with a really good strategy for the early parts that are coming up and just estimate how to play in the later parts. When we find ourselves in another subgame, we again compute a much better strategy in that particular subgame using information about the expected values of the other subgames. And that's called nested subgame solving. And this was the key breakthrough that allowed us to beat top humans. Yes?
Just concretely in this picture, so is this like each flop or each round of betting is...
Yeah, so that's a great question. So actually when we do this is sort of like a general, how we would do this in general. But in poker, we solved the first two, there's 4 betting rounds. So we solved the first 2 with a pre-computed strategy, because it's like each round grows exponentially in size. So the first 2 rounds are actually pretty small. When we got to the end of the second betting round, that's when we applied subgame solving. So we came up with a much better strategy for the remainder of the game. We abstracted the bets. So we wouldn't consider all the 20,000 different bet sizes. We would just consider a small fraction of them. And then each time the opponent acted, each time they made a bet, then we would solve a new subgame for that bet size. So we would apply this recursive solving thing every time the opponent made an action beyond the second betting round. Okay, so when I mentioned this idea of what's called safe subgame solving, where we use the expected values from the other subgames, people always ask about this thing called unsafe subgame solving, which is the more intuitive approach to doing this. The idea here is, well, why don't we just estimate what the opponent's strategy is, right? Let's say we can sort of we played a bunch of hands against them, or we can estimate what the Nash equilibrium is for them, and we figure out, well, they should be choosing play 80% of the time when the coin lands heads and play 30% of the time when the coin lands tails, let's say, just for example. And now, if we assume that the opponent is playing the strategy, can we then reason about the distribution of states that we might be in, and then solve optimally using that distribution? And it turns out that doesn't work. So let me give you an example of what this would look like. When the coin lands either heads or tails, we reason that we are in one of these states with 50-50 probability. And now if we observe player 1 choose play, we would say, okay, well, in a Nash equilibrium, we would expect player 1 to choose play 80% of the time if we were in the left state, 30% of the time when we're in the tail state. So we update our belief about what state we are in using Bayes' rule, and now we can reason that we're in that left state with 73% probability and in that right state with 27% probability. And now we would just say, well, if we assume this distribution is correct, then the optimal strategy is to always choose heads. But we've already established that that's a really bad idea, because now the opponent can simply shift to slowing the coin when it lands heads and choosing play when the coin lands tails. And so the problem with this approach is that we're making an assumption about how the opponent is playing. If it were true, like if this distribution were true, that they were choosing play with 80% probability and in heads and 30% probability in tails, then yes, we could apply this reasoning. But the opponent's strategy can always change. It can always change adversarially to us. Yes?
That's one of the things I've always been interested in, is whether you play the Nash or you play against the opponent, right? It seems like they're not going to shift. Even if you were playing the wrong strategy, they wouldn't exploit it up immediately, right? They'd have to learn to exploit it. I guess it's safe to definitely model the Nash, but I am curious about this intermediate space where you play against how they've been playing in the past, recognizing that you need to shift in some way because they may shift as well.
So, yeah, that's a great question. We actually did not. So one of the interesting things about humans playing poker is that they're actually really, really good at exploiting. They are phenomenal at it, way better than computers are currently. So we actually did a competition against them in 2015 where we lost. And we would sometimes change the bot that they were playing against between days. And within like 50 hands of playing, they could figure out how the bot had changed. So, yes, if you could make an AI that could figure out how to do this better than humans, then that might be valuable. But we're playing against really talented humans, and we didn't think that we could beat them at that game. But then also, why bother playing that game? Why bother trying to play that mind game if we could just approximate a Nash equilibrium and guarantee that we're going to win? So I would argue that in a two-player zero-sum game, if you want to beat top humans in a two-player zero-sum game, the best approach is to just approximate the Nash equilibrium, because now no matter what they're going to do, you're going to beat them. Now I would argue that if your objectives are different, so for example, if you really want to beat up on a weak player and exploit them, then yeah, you don't want to necessarily play the Nash equilibrium. You want to adapt to their weaknesses. This is challenging to do correctly, because if you try to adapt to a weak player's weaknesses, you never know if they're just fooling you, right? Like if you're playing rock, paper, scissors against somebody and they throw rock 3 times in a row and you say, well, he's clearly an idiot who's throwing rock every single time, I'm going to throw paper next time. They could just throw scissors, right? So, so there's no safe way, except in special cases, there's no safe way to do that kind of opponent exploitation and still guarantee that you're going to beat top humans in expectation. So I think that is an excellent avenue for future research. But I think that in the two-player zero-sum setting where we're just trying to beat top humans, I think this is the better way to go about it. All right. So unsafe subgame solving is very risky for this reason, because if you make an assumption about how the opponent is playing, they can always shift to a different strategy and take advantage of that. Now, that said, it turns out that this actually works. So we must account for the opponent's ability to adapt. Now, that said, in practice, unsafe subgame solving works unusually well in poker. It turns out that if you just approximate what the Nash equilibrium strategy is and then assume that the opponent is playing that and apply subgame solving in this way, that actually works really well in this domain. But we have found situations where this does not work well, and I think in more general settings, it would not do well. So we actually use this in a few situations in Libratus. But in general, I would not recommend doing this unless the domain is kind of specially structured that it would work. All right, so safe subgame solving, the idea is instead that we're just going to estimate what the expected value is for the opponent's subgames, for the opponent's actions for different subgames, and use that information to determine the optimal strategy for the subgame that we're in. Now, this works if your expected values are perfect, but if they're not perfect, you're obviously not going to compute an exact Nash equilibrium. So it turns out that there's room for improvement here. And this, by the way, this idea has been around for a while. It was first introduced in 2014. It was never really used in practice because it didn't actually give you good results in practice because you don't have perfect estimates. But what we came up with is a way to dramatically improve the performance without giving up any theoretical guarantees. We do something called reach subgame solving. So here's an example of how this works. This is going to get a little tricky. So if you have any questions in the next few slides, please let me know. So let's say that we have this slightly larger game now. It's still basically the same structure. There's a coin flip that only player 1 observes. Player 1 takes a sequence of actions. They eventually end up in this choice between selling the coin or choosing play. And now if they choose play, player 2 has to guess how the coin landed. But let's say our estimates are off in this game. Let's say we estimate that for choosing sell, they would get an expected value of -1, regardless of which state they're in. Well, the best that we can do is just guess 50-50 between heads and tails and guarantee that they get just an expected value of 0 for choosing play. But maybe we could use information about the earlier actions to improve upon this. So maybe there is this earlier action that player 1 could have chosen if the coin landed heads, where they could have gotten an expected value of 0.5. Well, that means that in the Nash equilibrium, they would choose that action and get an expected value of 0.5. And in the other case, they would come down here and choose play and get an expected value of 0. So they're getting an average of 0.25 in this game. But we can now shift our strategy as player 2 to ensure we guess tails more often, which guarantees that player 1 now gets negative 0.5 in this case. In the heads case, that means they would get 0.5 for choosing play. But that doesn't really matter because they're already getting 0.5 for this earlier deviate action. So we're not really giving up anything in this situation. We're just making ourselves better off. Because they would never get to the situation where they would choose the 0.5 anyway. And this seems really intuitive, but there's a problem with this, which is really subtle. And I'm going to have to go to a bigger game, which is going to get even more complicated to really illustrate it. Okay, so here is this bigger game. It's still pretty similar. The coin lands heads or tails with 50-50 probability. Player 1 in both cases now let's say has this deviate action. In the heads case, they can get 0.5. In the tails case, they get -0.5. Or they can choose to continue, in which case we run into this chance node. This chance node is public. It just leads to 2 different subgames. So both players observe the outcome of this chance node. It just leads to 2 different situations that are strategically identical. It's an irrelevant chance node, but it is a chance node. So, and then after this chance node, player 1, let's say, chooses play. And we estimate the expected value of them choosing play is now 0. All right, so let's say we're player 2 in this game. We observe player 1 choose play, which means that we are in one of these 2 different situations. Either the coin landed heads, they choose to continue, and let's say we observe that the chance node ended up going left, and then they chose play. Or the coin landed tails, player 1 chose to continue. We observe the chance node going left, and they choose play. So we're in either this situation or this situation. All right, well, we observe that they have this deviate action of where they could have gotten an expected value of 0.5 if the coin landed heads. So maybe let's say we say, okay, well, we can increase the expected value for this action to 1 and lower it to -1 in this case, for example, by always guessing tails. And that is okay because since this situation is only encountered 50% of the time, the expected value for this action is now just 0.5. And so that matches the deviate action, so we're not giving up anything. Does anybody see the problem with this? All right. The problem is, if that chance node had gone the other way, if it had gone right, we would apply this same exact reasoning. We would say, okay, well, we can increase this expected value to 1 because we're only encountering this situation half the time, so this expected value goes up to 0.5. And now the opponent's getting expected value of 0, and we're not giving up anything. But if we apply this reasoning, regardless of which way this chance node goes, then what that means is our strategy is to always guess tails in both situations. So in reality, it means that the expected value in this case is 1, and in this case is 1, which means that the expected value is actually 1. It's not 0.5. So now player 1 could be better off by choosing to continue instead of choosing this deviate action. And so what this illustrates is that when you are doing this subgame solving, when you're doing this real-time reasoning, you can't look at the expected values of what we call the blueprint strategy, the pre-computed strategy. You have to think about what the expected values would have been if we had entered that subgame and applied subgame solving there too. So that makes things way more complicated. But fortunately, with reach subgame solving, and by the way, so 2 prior papers had actually discussed this idea of, okay, well, we're encountering this situation, let's just increase the expected value for here, because they could have gotten an expected value earlier on, and sort of missed this problem that you have to consider about all the subgames that people could end up in. So 2 prior papers published about this, and they both got it wrong. And our paper, NIPS 2017, recognized this problem and actually came up with a fix that allows you to do this reach subgame solving while still guaranteeing that your exploitability is not going to go up. And the basic idea is to just sort of only increase the expected value for both of these situations by 0.5. The actual details get a little bit more complicated, but they aren't too important for this talk. But the idea is you just sort of increase the expected values by less, depending on how many subgames they could end up in. You have a question?
Well, I was just wondering, I know this is like a really simplified example, but I was wondering if it's wrong versus just weird. Like, if you only increase, say, the values for the left of the public chance node.
Yeah, so let's say we're this
way
situation.
You first explained it.
Yeah.
It seems like this is still correct. It's just weird because you're sort of saying, like, if nature flips a coin heads, then I'm going to do this weird reaction, and if it's tails, then I'm not.
So I'll say this. If you are actually only increasing the expected value to 1 in this situation and keeping the expected value at 0 in this situation, that's totally fine.
Okay.
But you have to think about what would have happened. Like, imagine this from player 1's perspective. If we would increase the expected value to 1 in this situation because this chance node went left, and we would have increased this expected value to 1 if this chance node had gone right, then what player 1 is thinking is if they're in this situation, they're thinking that if I choose this action, regardless of which way this chance node goes, I'm getting an expected value of 1.
Yeah. If our algorithm actually did both.
Yeah. So that's what I'm saying, is that you have to think about what your algorithm would have done in all these other situations that didn't come up as player 2.
Okay.
Yeah.
Okay. I think I see.
Okay, so that's reach subgame solving. So the idea is for off-path actions, we have to consider how we would have applied subgame solving in all these other situations that didn't come up. We have a solution for it, which is basically to split that, what we call slack, among the different subgames. And we have a theorem that says reach subgame solving will not increase the exploitability of a safe subgame solving technique. And if there is these earlier actions where the opponent could have chosen a higher expected value, then it will actually improve performance relative to traditional safe subgame solving. And in terms of yes?
So can you go back?
Yeah.
So you only have to know the expected values for the subgames that are on the path, or on the paths from the...
That's correct. So you look at all the path... Yeah, so you look at all the situations where the opponent could have gone off path, and you have to know the expected values for those. Yeah.
What I'm confused about is what do you assume is correct related to your learning. So all of these are, because it seems that you're allowed to be updating some of these expected values, but then you're taking these purple as fixed.
Yeah, so maybe I should have clarified this earlier. So I'm assuming that we basically run an algorithm that approximates a Nash equilibrium for the entire game, and that's where these expected values are coming from. So we have this rough approximation of what the Nash equilibrium is for the entire game, and that's giving us expected values for all these different actions, but they're not perfect. It's sort of like, with Alpha 0, for example. Alpha 0 gives you, policy and values for all the different states that you might be in, but that's obviously not perfect, and you can improve upon it by doing Monte Carlo tree search in real time.
So what do you mean formally by the safe technique exploitability? So you assume that then the violet is off by a certain fixed delta?
That's a great question. So by safe subgame solving, I mean that there is some exploitability. Our strategy, this pre-computed strategy that we have, is exploitable by some amount.
Assuming that all of these are correct, or they have...
Well, I'm just saying that we've run this, let's just say we've run traditional reinforcement learning algorithm on the entire game, no real-time planning, just pre-computed strategy. That strategy that we have now is exploitable by some amount. And I am saying that we would like to improve upon this in practice by doing real-time planning. But we want to guarantee that by doing real-time planning, we're at least not going to increase the exploitability of our strategy relative to what we had before. Now, in practice, it ends up being way lower exploitability, but we want to guarantee, we can't guarantee that it's going to decrease in most situations, but we want to at least guarantee that it's not going to increase. So that is what I mean by safe subgame solving.
So the purple is like the estimates from your pre-computed suboptimal value function.
Yeah, so those are the values that we've estimated based on our pre-computed strategy for the game.
You use those to compute the red, basically.
Yeah.
Okay.
So the red is the real-time planning expected values.
And so what's the running time of this kind of procedure?
I have not. For time reasons, I decided to not really talk about how we're actually doing all this computation of the strategy. We use something called counterfactual regret minimization, which converges to an approximate solution in 1 over square root t time. So if you do t iterations, you'll get within 1 over square root t of the Nash equilibrium. Okay.
Like in terms of the number of states and.
Oh, it is also, yeah. So it's linear in the number of information sets. In terms of, well, okay, so with Libratus, we actually used about several terabytes of data. And we used about millions of core hours of computation time. So.
You mean in real time?
Oh, in real time, no. In real time, it was way lower. So yeah, that was for the pre-computed strategy. For real time, it ended up being about we used about 1,000 nodes, or 1,000 cores, so about 50 nodes, and the memory is actually really small. It was probably less than 100 megabytes. We actually figured out how to improve upon this massively, which I'll get to in a little bit.
Is that 100 megabytes per core or per?
No, it's like the whole thing, 100 megabytes for the whole thing. Like the actual game, when you're solving from the turn onwards, like the third betting round to the end of the game, the actual size of the game is pretty small. But because you have to compute a solution, like an equilibrium for it, it takes a lot of computational power.
So was there like a limit on how much time you had to make a decision?
Yeah, we ended up doing it in less than 20 seconds or so. There wasn't like an official time limit, but we gave them some guidelines on how long it would take on average. Yeah. We also didn't give the humans a time limit, so if they wanted to take 10 minutes for a decision, then that was fine with us. I will also, one more thing about the time limit thing. So one of the interesting challenges of poker is that you don't want to give away timing tells, right? So if it takes you 2 seconds to make a decision, then the opponent might think you have a really easy decision, whereas if it takes you 2 minutes, then it might be a difficult decision. They can sort of figure out what hand you have. So if you're playing, if you look at the World Series of Poker, it gets really annoying because at the final table, they all take the same amount of time for every single decision. So they take 2 minutes for every single decision, even if it's a really trivial one. And we didn't want the humans to have to do this because it would have taken forever and it would have pissed them off, it would have pissed us off. So we told them flat out that the bot is not going to look at timing tells. So if they took 2 seconds to make a decision, that's totally fine. It wouldn't change anything. But we can't make them also do that for the bot, right? If the bot took 2 seconds versus 2 minutes, they would pick up on that and they can't not pick up on that, right? So we had to make the bot take the same amount of time for every single decision it made to prevent that. So that's also why it ends up taking longer to do this sort of thing. There are a lot of decisions that are easy, but we can't make that obvious. All right, so experiments on medium-sized games. So it turns out that our reach subgame solving technique that I just described is about 3 times less exploitable than prior safe subgame solving techniques. And nested subgame solving, this idea of applying subgame solving repeatedly as you go down the game tree, that is 12 times less exploitable than the prior state of the art, which is to just say, well, if the guy bet $60 and we have in our pre-computed solution a strategy for if he had bet $50, then we'll just round it and treat it as if he had bet $50 instead. That was the previous state of the art. So this is 12 times less exploitable than that in heads-up no-limit Texas Hold'em. In smaller versions of heads-up no-limit Texas Hold'em. Okay, so that is one reason for why imperfect information games are hard. There is a second reason that I wanted to get to, and I think I still have time to do it. This is more recent research. The second reason is that states don't have well-defined values in imperfect information games. So let me show you what I mean here. In a perfect information game and in single-agent settings, if you take some action, your opponent takes some action, you find yourself in a particular decision point, a particular subgame, you don't solve to the end of that subgame, right? You do what's called depth-limited reasoning, so the remainder of the game is too large, so you come up with a strategy for the next several actions, and then once you get to a certain depth limit, you say, okay, I've looked far enough, I'm just going to substitute a value for this leaf node and say the value of this arrangement of pieces on the board looks like player 1, white wins with 60% probability. So you assign a value to that state. And then you solve the depth-limited subgame using those values at the leaf nodes. And it turns out that this does not work in imperfect information games. I can give you a really simple example of why. This is a game that I call Rock, Paper, Scissors Plus. It is exactly like Rock, Paper, Scissors, except if either player throws, scissors? Yes, if either player throws scissors, then the winner gets 2 points and the loser loses 2 points. And that's just to break the symmetry of the game. So the Nash equilibrium in this game is to throw rock and paper with 40% probability each, and scissors with 20% probability. Now I want you to imagine that we're trying to do a depth-limited version, a depth-limited solving of this game as player 1. So we look one move ahead, and then we're just going to substitute the Nash equilibrium value at each of those states instead of going to the end of the game. This is the depth-limited subgame. And it's really easy to see that if we were to try to solve this depth-limited subgame, there is no way that we're going to find that optimal strategy of 40%, 40%, 20%. Right? There's just not enough information in this depth-limited subgame to find that Nash equilibrium. And why is that? Well, it turns out the reason is because we are essentially assuming that beyond this decision point, player 2 is going to play the Nash equilibrium strategy. Right? That's where we got the 0, 0, 0 from. This is assuming that if we had chosen scissors and player 2 plays the Nash equilibrium strategy beyond this point, this expected value is 0. But in reality, player 2's strategy beyond the depth limit depends on what our strategy is above the depth limit. If we choose rock 80% of the time, player 2's strategy isn't going to be to play the Nash equilibrium. It's going to be choosing paper 100% of the time. So this is what the state values will look like. Or if we were to choose paper 80% of the time, then they would switch to always choosing scissors. And this is what the state values would look like. So in an imperfect information game, the values of the states of the depth limit depend on what our policy is in the earlier parts of the game. So how do we deal with this? Well, one option is to just actually make the state values dependent on our policy and say, okay, well, the value of a state is a function of the description of that state and our policy for the entire game. Well, that is theoretically correct, but the problem is that that's extremely expensive. I mean, absurdly expensive. The other option is something called, actually, you might have heard about this AI called DeepStack. They condition the value of a state on the belief distribution of both players at that state. So they said, okay, well, at this decision point, I'm not going to condition on the strategy for the earlier parts of the game. I'm just going to look at all the different states that I might be in and the probability that I believe I'm in each of those states, which in this case is 80%, 10%, 10%. And in this game, it ends up being the same exact thing as just conditioning on the policy, but in general, that's not the case. The problem is that this is still extremely expensive. So DeepStack, for example, in Heads Up No Limit Texas Hold'em used 1.5 million core hours of computation and could not beat prior top AIs. The other problem is that the technique currently does not scale to larger games, basically games where you have more states in an information set. You can get by with this in Heads Up No Limit Texas Hold'em because there's only about, in any single decision point, any single information set, there's only about 1,000 different states in that information set. But in a game like 5 Card Draw, for example, there could be 5 billion. Or in a game like Stratego, there could be 10 to the 20th or something. So this would not work in those larger games. So what we do instead is this paper that we just had accepted to NIPS for 2018 called Depth Limited Solving. We use this in an AI we created called Modicum. Let me walk you through the algorithm here. The idea is instead of assuming that there's a single value at this depth limit, we're actually going to let the opponent choose between multiple different values for these states. And we do this, we create these different values in an iterative process. So we start off by assuming that player 2, beyond the depth limit, is just going to play the Nash equilibrium strategy that we pre-computed. And then we solve this depth-limited subgame. which in that case means, let's say we solve it and we say our strategy is going to be 1/3, 1/3, 1/3 probability. And now we're going to calculate a player 2 best response. So we can say, okay, well, if our strategy here is to play 1/3, 1/3, 1/3, player 2 could exploit us by always choosing rock. And now we add that best response to the set of strategies that player 2 can choose at the depth limit. So now we're going to solve this depth limited subgame again. And we're going to say at this depth limit, now player 2 can choose. So they can either choose the Nash equilibrium strategy that we had before, or they can choose this best response that we just calculated, which was to always play rock. And they make this decision because all these states share an information set. They can't say, okay, well, in this state, I'm going to choose this policy, and in this state, I'm going to choose this policy. No, they have to make the same decision at each of these different states that share an information set. So we solve this depth limited subgame again, and then we again calculate a player 2 best response to that strategy, and then we add that strategy to the set of best responses that player 2 can choose at the depth limit. And we can repeat this process as many times as we want. Now, some details about this technique. It might seem like this is really expensive. It might not get good performance because we can't add like a million different strategies for player 2 to choose at the depth limit. But it turns out that because they are making this choice separately at each information set, they are essentially able to, even if we only give them a choice between 10 different strategies beyond the depth limit, if they are making that choice individually at 100 different information sets, they're actually choosing between 10 to the 100 different strategies for the entire remainder of the game. So it actually grows very quickly. The other thing for player 1, I talked about what player 2 does. So player 2 is choosing between these different strategies that they could play for the remainder of the game. Player 1, we're going to assume, is just playing the approximate Nash equilibrium. Player 1 is us. We're just going to assume that we're playing according to the approximate Nash equilibrium strategy for the remainder of the game. And the set of player 2's strategies is pre-computed. It's not determined in real time. That you could do it in real time, it would be too expensive in practice. Okay, so this is what performance looks like if we do this depth limited solving thing. So on the x-axis here, we have the number of values per leaf node that the opponent can choose between at the depth limit. And on the y-axis, we have exploitability measured in millibig blinds per game. And this is a simplified version of no limit Texas Hold'em that only has 2 betting rounds instead of 4. And you can see if we assume that each state has a unique value, which is essentially the Nash equilibrium value, like we would in a perfect information game, exploitability is extremely high. But as we add more strategies for the opponent to choose between at the depth limit, exploitability drops off very quickly. And in fact, with like 16 different choices, we're essentially at a Nash equilibrium. So the beautiful thing about this, yes?
So why is the F1, or shouldn't red and blue be the same?
No, because actually so for blue here, it's not doing any real-time reasoning. It's just doing this, like if they had bet $60, I'm going to round that to $50. So red is actually doing real-time reasoning, but it's assuming that each value has a well-defined, unique value.
So it's kind of like doing constraint generation on sequence trees or something. So what does it?
There are a lot of similarities between this and things like double oracle methods and things like that. Yes. All right. So in terms of head-to-head performance, the really cool thing about this technique is that it allows us to make a really, really strong poker AI using very few resources. To give you some perspective, we had this bot called Tartinian 8 that we made in 2016, which won the annual computer poker competition, which is a competition among poker AIs. It used 2 million core hours of computation, 18 terabytes of memory, and there was no real-time reasoning. We have Slumbot, which won that wasn't us, this was a different bot, that won the 2018 competition. It used 250,000 core hours, 2 terabytes of memory, no real-time reasoning. Modicum, which is the bot that uses this depth-limited solving, uses just 700 core hours, 16 gigabytes of memory, plays in real time with a 4-core CPU in under 20 seconds per hand, and it beats both of those other bots. So to put this in perspective even further, Libratus, which is the AI that we played against the top humans, used millions of core hours. I think it was something like 2 million or 5 million core hours, probably 20 terabytes of memory, and played in real time using like 1,000 cores. So we're able to get what is essentially probably superhuman. We haven't actually tested it against humans, but I'm pretty sure this is a superhuman poker AI, we're able to get basically superhuman performance using the resources in a laptop. And in fact, since I published this paper, I've just put another paper on arXiv where we figured out how to make this 3 times faster. So you could probably run it on a smartphone now. Yeah.
Why are the confidence intervals wide here? I would think that you could just run long enough to...
It turns out that there is a huge amount of variance in poker.
Yeah.
And because we're doing real-time reasoning and we're taking like 20 seconds per hand, the variance is massive. In fact, we trained this using 700 core hours. It took us like 1 million core hours to actually compute all these results. So the variance this has been a problem in the entire field, that the variance is just absurd. So this is a graph of head-to-head performance. Here we have Libratus, which beats top humans. Here is Modicum, which is the AI we just created that uses way fewer resources. Here are some other benchmark bots, our bot from 2016, our bot from 2014. Here is DeepStack, which is a bot from the University of Alberta, which actually has very low exploitability, but in terms of head-to-head performance, didn't end up being that strong. It also uses this real-time reasoning as well, though a different form of it. All right, so the key takeaways. Yes?
Wait, so you said that one doesn't have, it has low exploitability, but it's not that strong?
In terms of head-to-head performance, it's not as strong. So in terms of head-to-head performance, it actually doesn't beat prior benchmark bots.
Yeah, I guess that's kind of curious to me because, like, if you're not exploitable, okay, so you might.
Well, but when I say low exploitability, I mean just relative to the past bots.
Okay.
So like the exploitability is still, it could be extremely high. We actually don't know. We can't calculate exploitability exactly in a heads-up no-limit Texas Hold'em, so we don't know. But it appears that it has lower exploitability compared to the absurdly high exploitability of the previous bots. Yes. Okay, so key takeaways. In real-time planning, you always have to consider how the opponent can adapt to changes in your policy. That is something that is really important in imperfect information games. And perfect information games, you can mostly ignore that, but not completely. An imperfect information subgame cannot be solved in real time, cannot be solved in isolation. And states in imperfect information games do not have well-defined values. All right, so I have done some other work that I did not discuss. One thing I did not discuss, well, I guess I talked about it briefly, is how we actually solve these games. We use an algorithm called counterfactual regret minimization, which has been around for about 10 years now. Works extremely well, even though the theoretical guarantee on convergence is only 1 over square root t. I just had a paper that I released where I developed a new form of CFR which beats the prior state of the art by a factor of 3. So I'm really excited about that, and that's going to be used in all the future research. I have some work on pruning in CFR. So it turns out that CFR, you end up exploring the entire game tree, which is a big waste because a lot of actions are suboptimal and you don't want to waste time coming up with like what you should do if you play a really crappy poker hand because in reality you just fold it right away. So I have this pruning technique that provably reduces the computing and memory costs of running CFR asymptotically, and in practice it speeds things up by an order of magnitude or 2. I also have a paper on determining the optimal actions in a continuous action space. So one of the interesting things about no limit Texas Hold'em is that you have this continuous action space where you can choose to bet any amount between $100 or $20,000. And the truth is that what we do right now is just domain-specific abstraction techniques where we say, okay, well, you probably just want to bet either half the pot or 1 times the pot or 2 times the pot, and it doesn't really matter if you're betting 0.6 times the pot or 0.5 times the pot. But that relies on domain knowledge that we know the optimal bet fractions are roughly in that range. So it would be nice to have an algorithm that doesn't rely on domain knowledge that can actually determine the bets to use without any human knowledge. So that's what this 2014 paper does, and hopefully we'll have some follow-up work on that in the future. For future directions, so I mentioned before, like a lot of this work has been looking at poker as a domain, and that's because it takes a lot of infrastructure to actually build up to do experiments on large games. So we have a lot of expertise that has been developed over the years on how to run these techniques efficiently on a game like poker. And if we wanted to test on another large game, it would take years to build up that expertise on how to do experiments on those other games. There's also no other really good, we can't really compare performance to other bots in other games because there are no other games where there are bots that are competitive. But I would love to move beyond poker, and a few different directions for that. One is we have these techniques for perfect information games like AlphaZero, and we have these techniques for imperfect information games like poker. And it would be nice to bridge the gap and sort of find a single algorithm that works really well in all these different games. Another thing that I'm really interested in is going beyond two-player zero-sum. So I mentioned that if you try to move on to general sum games, there's a bunch of theoretical challenges that pop up. And so right now we don't know how to cope with those challenges. But dealing with general sum games is really important because most real-world situations are general sum. They're not zero-sum, except for like maybe military interactions or security. So in particular, working on something like negotiation, I think is a really interesting line of research. And in general, moving things more towards real-world domains, I think we're at the point right now where we can actually start bringing these techniques into the real world. And I think that's going to be a really interesting line of research as well. All right, so I'll stop there and I'll take some last-minute questions. Thank you. Yep.
Yeah, so I guess in the real world, often you don't know the rules of the game. You don't know them in advance. It's not a simulatable situation.
Right.
But you do observe the outcomes of plays. So have you thought about trying to, what works and what breaks when you go into a situation where you don't know the rules of the game, but you can't observe the outcomes of plays?
That's a good question. So yeah, so all of our work assumes that we have an accurate model
Right.
of the world or the game that's being played. I think a lot of these techniques will carry over if you want to try to figure out the structure of the game as you go. There was actually a paper from another student at CMU recently on this problem. So people are starting to look in this direction. I have not, but it's something that I think is very interesting. It is also a way harder problem because to figure out like what information your opponent knows, or knows, like figuring out what they could know, is a really difficult challenge. Yeah, I'm not sure how to go about that. Yep.
I think I've got any applications in something like safe reinforcement learning. So right now, I can imagine splitting the environment into the portion which I can model. That would be kind of like chance moves. And then and then parts that I don't necessarily want to model because I'm very risk averse. So that could be kind of like adversarial moves. And I want to be robust to both. Have you thought about how well your techniques would apply, or just completely out of the ballpark?
Yeah, to be honest, I've never really considered that direction for the research. I think there's a lot of potential here. I mean, this is like an area of research that I think has been overlooked by a lot of people. So there's actually been a very small community that has been working on this space, and I think people are starting to appreciate that it can be applied to a lot of different things. And we're starting to see papers on how to apply, something like counterfactual regret minimization to more mainstream reinforcement learning topics. So I think there was a paper from Berkeley recently on regret minimization in like single agent settings. So I think there is definitely potential to extend the research into the more traditional reinforcement learning settings, but I have not looked into that yet. Yeah.
I don't know, this might be a naive question, but maybe following up on John a little bit. Is there anything I'm learning? So in the real world, one of the things I think it's really difficult is I don't know the rules of the game. I also really have no idea what my opponent's payoffs are, often.
Mm-hmm.
Is that something that people have looked at? Trying to like basically think about simultaneously trying to improve my own payoffs, but also trying to get some better model of what's going on with the opponent?
Yeah, I guess that would be kind of a subset of the previous case we discussed, where it would be like maybe you know the structure of the game, but you don't know the opponent's payoffs. I think this has been looked at in the game theory community, but more in simple cases, not like large-scale computer science settings. So I could be wrong about that. I don't know too well.
As you said, I thought, well, I should know the game theory. Yeah, sure. So there are models where like there's an opponent type and it's unknown, but the type parameterizes the payoff function.
Yeah,
Sure.
yeah. So I don't know of any large-scale work on that sort of thing. But that also, I think, that seems like it would be a lot easier to extend this work to that domain than to just not know the rules of the game at all.
Yeah.
Yeah. Okay.
Thank you.
Thanks.